In this video, I'm going to talk about input impedance and reflected impedance. Okay, so here is an ideal transformer, transformer with two coils. Okay, these two lines indicates it's an ideal transformer. Okay, now the input impedance is nothing but Z input, which equal to V input over I1. So when we look at this circuit, what is the total impedance of this circuit when we are looking from these two terminals, input terminals? That's what the input impedance is. The reflected impedance is nothing but what we can do. We can transform not this whole thing, we can transform this whole thing. Okay, this whole thing is nothing but the impedance on the secondary side into the primary side of the transformer. So basically when I transfer, this is what we're going to have. V input, okay, I have resistance and L1. Okay, now the total impedance of the secondary converting, or total impedance of the secondary transferring to the primary side, we call that as reflected impedance. Reflected impedance is nothing but impedance of the secondary reflecting on the primary side. Okay, so we'll find what is ZR and we'll find what is ZN in this video. So loop 1, I'm going to take this as loop 1, apply KVL in loop 1. Loop 1, apply KVL. Before applying KVL, make sure everything is in frequency domain. So this is j omega L1, this is j omega M, j omega L2, and that's a ZL. Okay, so KVL minus VN equal to R1 I1 plus j omega L1 I1 plus there is a voltage across L1 because of the current flowing in the secondary. Okay, so if you look at I2, is current is entering the dot or leaving the dot? I2 is leaving the dot, so the dotted terminal must be minus and plus. There is an induced EMF. In previous case, I have plus minus, but here I end up with opposite sign, so this must be minus j omega M I2. This is my first loop equation. Okay, I'm going to explain one more time how did I get this. So here, so if you look at loop 1, I'm sorry, this must be positive here. I don't know why I put that equal to 0. Okay, so if you look at loop 1, I'm entering the negative terminal, so minus Vn. So I'm following this direction, I1 plus minus. So I'm entering the positive side, so plus R1 I1 plus j omega L1 I1. Now if you look at the dots on the secondary side, my I2 is leaving the dot, so the dotted terminal must be minus, so I'll end up with E2. Okay, so this is opposite sign, so that is the reason I end up with negative there. Okay, that's loop 1. Loop 2, apply KVL. So if you apply KVL in loop 2, let me write down loop 2 here. Okay, here is my I2 according to my I2 direction. Positive, negative, positive, negative, positive, negative. Okay, so this is L2, j omega L2 I2 plus R2 I2 plus ZL I2. Now there is a mutual inductance because of I1, so here is the dot. I1 is entering the dot, so the dotted terminal must be positive here. So that value is, now I have the opposite sign, so it must be minus j omega M I1 equal to 0. This is my second equation. Now I have two equations, two unknowns. Okay, so this is my second equation, this is my first equation. Now the second equation, I'm going to write down everything in terms of I1. So j omega M I1 equal to j omega L2 I2 plus R2 I2 plus ZL I2. Okay, so I1 equal to, I'm going to take out I2, we'll end up with J omega plus J omega L2 plus R2 plus ZL divided by J omega M. Now I'm going to take, actually I need I2 value so that I can substitute it here, so that I can eliminate I2 in there. All I need Vn over I1, so I'm going to put it I2 equal to J omega M I1 over J omega L2 plus R2 plus ZL. This is my I2. Now I'm going to take this I2 and substitute it in this equation. So minus Vn, or I'm going to take it Vn on the other side. So Vn equal to R1 plus J omega L1 I1 minus, so here I have J omega M. Now I'm going to substitute I2 equal to J omega M I1 over J omega L2 plus R2 plus ZL. Okay, now J omega minus J omega M minus J omega M whole square, so we know that minus J square equal to positive 1, so it's going to be Vn equal to R1 plus J omega L1 I1 plus omega square M square over J omega L2 plus R2 plus ZL times I1. Okay, so now I1, I have common term there, so Vn over I1 is nothing but the input impedance, Zn equal to R1 plus J omega L1 plus omega square M square over J omega L2 plus R2 plus ZL. ZL is the load impedance. Okay, so this is called input impedance. Okay, all of it, this is the input impedance is this is input impedance. Now the reflected impedance is nothing but, this is the reflected impedance. Reflected impedance is nothing but impedance of the secondary looking from the primary side. Okay, so ZR is nothing but impedance of secondary looking from the primary side. So my ZR reflected impedance equal to omega square M square over J omega L2 plus R2 plus ZL. This is called reflected impedance. The next topic is equivalent T network. Okay, so if you take this two circuit, if you take this circuit, here in this circuit I have two inductors magnetically coupled by a mutual inductance of M. What I can do, I can convert this into a T equivalent circuit. This look like a T, so if you look at here, this look like a T. That's the reason we call this as T network or T circuit. Okay, both of them are same. Now if I connect these two here, it's not going to make any difference because there won't be any current passing through this all the time. Okay, this is going to be grounded there, this is going to be grounded there, so connecting this will not make any changes in the circuit. Now, so this two inductor circuit or mutual circuit, so or magnetically coupled circuit, I'm converting this into electrically coupled circuit. Okay, this look like a T, so that's the reason we're calling it as T network. So here LA, there is a derivation in the textbook. I'm not going to go over the derivation, but I'm going to give you values. LA equal to L1 minus M, LB equal to L2 minus M, and LC equal to M. Okay, this is the T network. We can represent another network called pi network or pi circuit. I'm keep calling network because this T network and pi network, we use it a lot in the electronic circuits. Okay, so there, instead of circuits, they call it as networks. Okay, but network and circuits, there's a little bit different, but almost same. You can call a network as a circuit, but you cannot call a circuit as a network. A big small difference. Now the pi network is going to be something like this. Oh, another important point here at the T network, make sure both currents are entering. I1 and I2 are entering. So the pi network, it's going to be look like pi. See, it's look like a pi. We call this as pi network. Okay, so here this is LA, LC and LB. Here also this is my V1, V2, both currents are entering. I1 and I2, both of them are entering. Now the equivalent LA equal to L1 L2 minus M square over L2 minus M. LB equal to L1 L2 minus M square over L1 minus M. And LC equal to L1 L2 minus M square over M. These are the LA, LB, LC of the pi network. So now, I mean, there is a derivation. I'm not going to ask you to derive this. Do you need to remember this? You don't need to remember, but it's a good idea to write down in that one page of notes for the exam. Okay, so here I showed you a magnetically coupled circuit converting a magnetically coupled circuit into electrically coupled circuit. Same thing, you can convert that into a T network, or you can convert this into a pi network. So when you convert this into T network, LA equal to L1 minus M, L2 minus M and M. Here when you convert this into pi network, LA, LB, LC are given here. Okay, I'll stop this video here. Next video I'll solve examples based on the transformers. Thank you.